In this particular video, we are going to describe about the Lambert law, which is the laws of light absorption. However, the light absorption is governed by two important laws. That is, the amount of light absorbed by a material is governed by two important laws. One is known as the Bouger Lambert law, or simply called the Lambert law, and the second one is known as the Beer's law. Let us first understand what is the Lambert law. Say we have a sample container here, and the thickness of the sample container is say 1 centimeter. So the thickness of the sample container is say 1 centimeter, and now we are passing a light through this sample. So the sample may contain protein molecule or nucleic acid molecule like that. Say it is a protein molecule. We are adding bovine serum aluminum, that is BSA. We are adding BSA into it. So the BSA molecule contain several carbon, hydrogen, nitrogen, oxygen atom, etc. inside it. So when we are passing a light, that is the incident light, if we say the incident light is the I0 incident light through the sample will definitely absorb some amount of light, and after that say it is absorbing 25% of incident light, it is absorbing 25% of the incident light. Then the transmitted light means the light that is coming out from the suspension. The light that is coming out from the suspension is known as the transmitted light. If the transmitted light is denoted by I, that is transmitted light, then what will be the transmitted light? Definitely the transmitted light will be 75%, right? Why? Because always the incident light is 100%. Whatever the light you are passing through the sample, it should be 100%, and after that the sample molecule will absorb some amount of light. In this case, we are saying that it is about 25%. 25% of the incident light is absorbed by the bovine serum aluminum molecule. In that case, the transmitted light will be 75%, right? So if we increase the thickness of this absorption material, so if we increase the thickness from say 1 centimeter to 2 centimeter, say we are increasing the thickness from now 1 centimeter to 2 centimeter, that means the path length is increased double from the initial amount. In that case, now there is every probability that when the incident light is going through the sample, which is always 100%, now the sample will absorb more because the thickness has been increases. For example, in the first case, say in this line the total sample molecule was 4, and the sample molecule is present here and there. Say these are the sample molecule present on the surface, there are some sample molecule present at the bottom, but the light is passing through these four sample molecule. But whenever we are extending the path length, whenever we are increasing the path length, in that case there will be more amount of sample molecule coming from the upper part or from the bottom part, right? In that case, the number of absorbing molecule will be increases. So therefore, in that case, the transmitted light is definitely not the 75%, it may be 50%, because now the molecule is absorbing 50% light. So this is the idea that we can represent this thing in a different way. That say we have the same kind of this thing. We have one container which is normally known as the cuvette in spectrophotometry, which is about B centimeter path length, and the molecule that is present within the sample is absorbing 50% of light, 50% of the incident light. In that case, I0 is 100 and I, that is the transmitted light, will be 50%. It's a very simple theory. And now if this light is passing through another container of same path length, that is B centimeter, in that case the transmitted light from the second container will be definitely 25%, and so on. If we do this thing for another cuvette having the same path length, say B centimeter, in that case the transmitted light will be here 12.5%. So this is actually known as the Bouger Lambert law, that is the Bouger Lambert law, Bouger Lambert law. or simply it is called the Lambert law, which says light absorption of any molecule is totally independent on the intensity of the incident light. So it is the intensity of the incident light is always 100%. We are saying that I0 is always 100%. So the amount of light absorbed by a material is independent on the intensity of the absorption, intensity of the incident light, but is directly proportional to the path length of the absorbing material. The light absorption is directly proportional to the path length of the absorbing material. That means more the path length, the greater will be the absorption. So we can write this thing in a mathematical way, that is, say if this law is true, that is the amount of light absorbed is directly proportional to the path length of the absorption material. In that case, we can write that is I is equal to I0 into e to the power of minus AB, where I0 is the intensity of the incident light, I is the intensity of the transmitted light, and K is the absorptivity constant, and B is the path length of the material. This is the path length. Path length means thickness. Thickness is the path length. So we can rearrange this thing, that is I by I0 is equal to e to the power of minus KB, or ln I by I0 is equal to minus KB, or you can omit this minus sign, that is ln I0 by I is equal to KB. ln means 2.303 log 10 base I0 by I is equal to KB. So this is the ultimate mathematical expression of the Lambert law. Now the next law, which is known as the Beer's law. So Beer says that, say we are adding BSA in the solution at a concentration of say 1 mg per ml, and in that case they are absorbing say 25%. When the concentration of the bovine saline aluminum is only 1 mg per ml, they are absorbing 25%. So if we increase the concentration, in that case the number of molecules through the path length will also be increases, right? If we increase the concentration of the BSA from 1 mg to 2 mg per ml, say, in that case doubling the concentration actually doubles the number of biomolecule present through the path length of the incident light. In that case the more will be the absorption. So Beer's law says that the amount of light absorbed by a material is directly proportional to the concentration of the absorbing molecules. So Lambert law says that it is proportional to the path length of the absorption material, and the Beer's law says that the light absorption is directly proportional to the number of absorbing molecules present within the sample, that is nothing but the concentration of the absorbing molecules. So it's a very simple idea. If we increase the concentration of any biomolecule, they will absorb more. So we can rewrite this expression in the form of Beer's law, that is, if Beer's law is true, then I is equal to I0 into e to the power of minus Kc, or K dash C, we can write K dash C. In this case I0 is the again intensity of the incident light, I0 is the intensity of the transmitted light, K dash is nothing but the absorptivity constant, and C means the concentration. So by the similar approach, the ultimate statement is definitely will be 2.303 log of 10 base I0 by I is equal to K dash C. So this should be the ultimate statement of what is known as the Beer's law. Beer's law or Beer law, right? Beer's law. So now we can combine these two laws, the combined law. So combined law says that the amount of light absorbed by a material, which can be denoted by absorbence or transmittence, the amount of light absorbed by a material is proportional to both the path length of the absorption material and also the concentration of the absorbing molecules. So we are combining the two laws. The Lambert law says that light absorption is totally proportional to the path length of the absorption material, and Beer's law says that light absorption is proportional to the concentration of the absorbing molecules. So if you combine these two laws, you have the concentration and you have path length of the material. So by combining two laws, the amount of light absorbed by a material is proportional to the concentration of the absorbing molecules and also the path length of the absorption material. So this is the combined law. So we can take together, we can take these two laws And if we join these two ultimate statement of the only Lambert law and the only Bouger law, then we can cancel out this 2.303 term. So we can rewrite the combined law. That is a combined statement. From combined statement, what we can write? We can write log of 10 base I0 by I. We are eliminating 2.303 term. We are taking only log of 10 base I0 by, because in both cases they are present. And we have this k dash constant and also k constant. So two constants are there. We can rewrite the two constants in a single constant, that is known as the small a. And now we have the path length, that is known as a B, and the concentration known as a C. So this is basically the combined law, which is also known as the absorbence. A, capital A stands for absorbence, or you can say OD. So we are taking OD whenever we are putting some sample in a spectrophotometer and we are transferring light to the sample. We are actually measuring the absorbance or OD. Okay. So the two law says that according to Bouger's law, we can make a graph. That is, if we take OD with respect to concentration, if we plot OD with respect to concentration, the more the concentration, the greater will be the OD. In that case, you have this kind of graph. Because the more the concentration, say 1 mg per ml and 2 mg per ml, 3 mg per ml, 4 mg per ml, 5 mg per ml. So the more the concentration, the value of OD will also be increases, right? So these are the points. OD value, the absorbance value. So we can also measure the transmittance. What is the difference between absorbance and transmittance? The transmittance is equal to 1 by absorbance. Transmittance is equal to 1 by absorbance, that is equal to log of I by I0. So whenever you are calculating log of I by I0, then you are going to calculate the transmittance. And when you are going to calculate log of I0 by I, that is equal to ABC, that is, then you are going to calculate absorbance, that is equal to, also known as the OD. Now you have idea what is B, that is the path length, or what is C, that is the concentration, but what is actually A? A is known as this small a, it is not the capital A, remember, it is a small a. This small a is known as the absorption coefficient. Or you can say it is the extinction coefficient. So this is a vital thing. You have to determine absorption coefficient and extinction coefficient to determine the absorbance. What is the actual absorbance of any biomolecule? So these two laws, that is the Lambert law and Bouger law, the combined law, what is also known as the Lambert-Bouger law, simply called the Bouger law. This is a vital portion whenever you are studying some biomolecule. What is the biomolecule? You are isolating some biomolecule from nature and you don't know what is the biomolecule. You need to identify which biomolecule it is. For example, if it is a protein molecule, then you require this absorbance, you require this two law, because protein will maximally absorb at 280 nanometer. So you have to transfer the whole wavelength starting from 180 nanometer to say 780 nanometer, and you are passing the each and every wavelength through the sample, and you can get a peak, particular maximum peak, lambda max at a particular wavelength. Say it is 280, then you can say it is protein molecule. If you are getting lambda max at 260, it is a DNA molecule. So by this way, by qualitative analysis, you can determine that what is the sample present in it, and for this you record this Lambert-Bouger law. And if you want to quantify the sample, that is, you know that it is a protein, you know it is the nucleic acid, now you want to measure what is the actual concentration of the molecule present within the sample. You have also do this thing by using spectrophotometry. So the basic law of spectrophotometry, or the light absorption law, is the Lambert-Bouger law. Hope you have understand. In the next video, we will describe about what is the extinction coefficient and the different types of extinction coefficient, that is the molar extinction coefficient and specific extinction coefficient, and how the extinction coefficient can be determined. Hope you have understood.